yeah, so if you don't have access to NERSC, yeah, actually, for people that do not have access to NERSC, I have prepared some executed notebooks. So you could take a look at them, okay? So while we execute stuff interactively. So let me share the link on the chat. So let's see. Okay. Oh.
And for the people that don't have access on NERSC, if you're interested in getting an account, please do reach out, and I can give you instructions to make a NERSC account.
So if, yeah, another option for the time being, just to follow along with the tutorial, at this link that I just pasted on the chat, you have notebooks that have been already executed, okay? Because in the repository here, all the notebooks are empty, so it's more difficult to follow along. But if you want to look at those notebooks, you can just use your browser. All the notebooks there are already executed, so you can look at the plots, and while during the tutorial we'll be playing with the notebooks interactively. Okay, so it's 10:30, so this is the last call. If anyone wants help in setting up the kernel, otherwise we're gonna start. So anyone else has trouble, please unmute yourself or ask on the chat, because we're gonna start otherwise. Okay, very good. So I think we can get started. Okay, so I'm probably going to talk about 50 minutes on the first 5 notebooks, and then Matt is going to show you the last 2 notebooks on the car pixelization. So I assume that everybody has the environment set up. Also, I wanted to mention that it's Black in Astro week this week, and there are very interesting articles on Astrobytes, if you want to take a look at those after the tutorial, or on Twitter there are a lot of posts about Black in Astro. Okay, so this, let's start with this just to test the environment. So you should be able to execute this fine, okay? So this is just to check that all the packages are importing fine, and that you're using the right kernel. So I assume that everyone is okay here. If not, please write in the chat and maybe someone else can help you out. I will go ahead and start the actual lesson and notebook number 1. So if you open from the file browser here, you open the notebook number 1, foreground CMB. And then it's useful to also open the table of contents. You see down here on the left, the table of contents plugin that gives you the structure of the notebook. It's very useful if at some point you get lost and you don't know where we are. Okay. Okay. So if you are not familiar with the notebooks, you click play, the play button here to execute a cell, or you do Shift Enter. Okay, and so as I go along, we will be executing code. Okay, so for this first notebook, what we want to do is we want to take a look at existing map-based simulations releases. So for these releases, so the central point is this GitHub repository. Okay, so whenever you need information about MBS simulations, you can go here. So you see there is a list of available simulations. So I clicked on the link to go to the repository. And here you can find information about all the releases and documentation on how they were executed and where are the inputs components coming from, and the path at NERSC to retrieve the executed maps. And so let's start, and it's also very convenient to use the MapSims package, which is the package that I developed to execute the simulations, also to handle metadata about Simons Observatory. So for example, you want to loop through channels, you want to find the beam of a channel or the center frequency. This is already all available through MapSims, and so it's quite a convenient interface, okay? So you see the first entrance point is the parse channels function. So you give it a specification on which channels you want to use. So if you want one specific channel, you can just use just the name of that channel. Or if you want all the channels in a tube, you can specify tube. And there is extensive documentation about this package. So you can take a look at the at the repository of MapSims. There is documentation. MapSims is still under the Simons Observatory GitHub organization. So github.com/simonsobs/MapSims. Okay, and so for example, you see here this created a two-channel object, and then within the channel you can access the channel properties. So you can do channel.beam, and you get back the beam. And you see that this also works with units. So if you haven't used AstroPy units before, it's a little tricky at the beginning if you're not, because you have to learn how to handle those, but it's very convenient because it makes it a lot cleaner and avoid some errors, the typical errors where you thought you were using arcminutes, instead they were degrees. Okay, and so you see you can do unit conversions, okay, you can filter by telescope, and the nice thing is that with the same interface, we can also access metadata from other channels. For example, all the Planck, so if you specify the instrument parameters from Planck, then you're going to get the Planck channel. So if you're doing some joint analysis, this could be useful. So you see here we are looping in the same loop through all the Simons Observatory channels and also all the Planck channels. So you see all the Simons Observatory channels here, and then printing out also the beam and the center frequency, and then Planck below. Okay. Another very useful feature, which is this is actually implemented in PySM3 and not in AstroPy, is that we can do conversion between Kelvin CMB, Kelvin Rayleigh jeans, and Jansky's best radian. Okay, so you see here, you basically do the conversion with the two method, and then you provide the frequency where you want this transformation to be executed at using the CMB equivalencies function. Okay, so you provide the frequency, you want to do this conversion, then this is going to do your conversion. And this works also for array, so you could have a map in KCMB and convert it to RJ with this. Okay, so now let's try to access the maps. Okay, so you look at the documentation, you find out that the latest release of foregrounds and CMB is at this specific path at NERSC. Okay, if you look at the documentation on that GitHub repository, and now we are at NERSC, so we can access those directly. And so you see here, we have a folder for each component, and then a folder for all the combined components together. And then in the page of the release, you also get a file name template. So you just copy paste your file name template, and then you fill in with all the things that you want to choose from. Okay, so the channel, the most important thing is the channel band and the channel telescope that you want to use. Okay, and then you get your full file name, and then you can read it standard with HillPy functions. Okay, so for example, I loaded the combined map for the small aperture telescope ultra high frequency 1 band, and then I just compute the polarization and plot it. So you see here that all the foreground simulations are full sky. Okay, that's because sometimes we want to use different scanning strategies for Simons Observatory, so you can apply any cut that you wish later on. Okay, so but the maps themselves are full sky and they have IQ and U polarizations, of course. Okay, and as part of the releases, we often provide also some masks that are these maps. I think they are released from the foreground group. So map-based simulation, we gather all the input from other teams and then we package them for a release. Okay, so you see we have loaded some standard mask and then we can apply this mask, this galactic mask to our map. And the most important one instead is to apply a scanning strategy. So what we want to do is we want to actually see what the maps looks like for an actual Simons Observatory channel. And in this case, we call another part of MapSims, which is the noise simulator. So the noise simulator is the object that handles both the noise, so is able to simulate the noise, but while we are simulating the noise, we interface with the expected noise curves, but also with the heat map, because we want to give a noise which is properly weighted with the heat maps coming from simulations. And so if you want to get the heat maps, you can access them through this interface. So you see, you create a noise simulator object at a specific end side that you wish, and then you can get the heat maps for each of the channels. Okay, and this works tube by tube. So MapSims, when we are talking about noise, always works tube by tube. That's because when we are generating noise, there is we expect that there is cross correlation between the two bands that are running on the same actual telescope tube, and so we always, for example, when we generate noise, we generate the noise for the two channels together, so that we can also simulate this cross correlation between the two. And the same thing goes with the heat maps. So when you call the heat maps, you're going to get the two heat maps for the two channels in the same tube. Okay. So for the time being, the two heat maps are the same. So we assume that they have the two bands in the same telescope have the same heat maps, but in principle they could be different. Okay.
Can I ask you a question?
Yes.
When you say tubes, do you also mean like if you're simulating the LIT? Just because I just wonder whether there actually can be some correlations, you know, between tubes in the LIT.
We don't. Yeah, we haven't. We don't simulate any of that. So we assume that every tube is independent.
Okay.
But yes, in principle, yeah, we could extend that, and but that would be a lot more complicated, of course, because generating high resolution maps for many tubes concurrently, it's complicated. But yeah, definitely that could be.
Probably it would be most likely to be a deal for LF, and then LF has very little atmosphere, so it probably is fine. Just curious.
Mm-hmm. Okay.
Okay.
So
simulate
yeah,
within a tube, between arrays within a tube, right? So that's where majority of the atmospheric correlation is going to show up, but not across tubes.
Okay, cool, thanks.
And Andrea,
okay.
you're not, you don't have a view of the raising hands, right? Should I interrupt you when I see a hand?
Yeah, yes, please, yeah.
Okay, sure.
Okay, okay, yeah. So you apply this cut with the heat map, so that you have the foreground. So in this map there is still no noise. So this is just the combined foreground. So basically all the components that were simulated. So starting from the CMB, but then also DAS, synchrotron, and all of the other components. Okay, all summed together. Okay, or you can load all, if you are interested in a subset of the components, then you can load the individual components and do the sum yourself. Okay. Okay, so is there any question on this first notebook before we go with the second? You can just unmute yourself and ask.
Andrea, if there are no questions, can I suggest to see if everyone is still following and everyone was able to run notebooks? We don't have to spend a whole lot of time again, just making sure that everyone was able to follow.
Yeah, so any trouble executing the notebooks, crashes or something?
Jesse, you had a problem?
Yeah, I can't get the installation of the kernel to work. I had accidentally logged out of my virtual environment. I reinitiated that, tried it again. I just sent you something on chat. But keep going. I mean, don't slow the group up.
Okay, so let's go with notebook number 2. Okay, so now we are going instead to access CMB realization. So if you look through the documentation, you also have a release of length CMB. So these are 100 realization of CMB maps length and with no with R equal to 0. And okay, so same thing basically. We load the maps, and so now I'm reading 10 maps. So I'm loading. You see here. So you specify when we have. So for the foregrounds, we just add 1 realization because they are deterministic. But for the CMB, instead, we have many realizations, and so you have a number here, which is encoded in the folder, and it's encoded also in the file name that gives you the realization number, basically. And so we specify this. We specify to load the first 10 realizations for CMB for 1 channel. And so you see this is inside 512. So all the LAT is inside, the small aperture is 512, and the LAT are 4096. Okay, and as we did before, we can apply a cut. Okay, so here we see just the CMB as seen from one of those channels with no noise still. Okay, so we can do a power spectrum. So we check that they are quite consistent. They come from the same input power spectrum. And then we can mix and match maps coming from different releases. They are all compatible. And so, for example, we want to add the dust to this map. So we go back to the previous notebooks. We get the path for one of those dust map, and then we can just add the 2 maps together. Okay. And so now we have a map which can have those CMB realization different. You can basically change CMB realizations and have some foreground on top. Okay. The difference in CMB is that the CMB realization in this notebook, in the notebook number 1, was a CMB realization that comes from the web sky simulations. So the web sky are dark matter simulations that are used to create the extragalactic components, and they also provide a CMB which is being lensed with the same potential that's used to simulate the extragalactic component, so that we have the expected amount of correlation between the extragalactic components and the CMB. Okay. Unfortunately, we only have 1 realization of that. Okay. So with the CMB lensed with the same potential as web sky. Instead, we have this set of 100 releases that are instead lensed with the random Gaussian potential. Okay. 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 So now at this
Andrea,
point,
sorry, Jill has a question.
Hey, Andrea, I have a question. So, so the maps, it seems like it has structures. What is stored in the map? I took a look. There were a list of masked maps, and then each of them has different layers. What are those saved things?
Oh yes, they were generated with different thresholds. You're talking about the masks, right?
Right. Yeah.
Yeah. So they have different cuts. So if you look at the documentation, is explained, and there is actually also the code that was used to generate those masks. Okay. So basically, cuts looks at the emission from some simulations and cuts when the emission is above some certain threshold. Okay.
I see. Thanks.
Yeah. So we try to document as much as we can in the GitHub repository. So from the GitHub repository of every release, there are often links to other documentation. For example, on the Python documentation, or for example, description of how masks were generated. And but yeah, if you find that anything is missing, please open an issue in the repository so that we don't miss anything. Okay. Is there any other question? Okay. So let's go with adding also the noise. Okay, so the strategy with noise is a bit different. So for noise simulations, we want to encourage people to simulate on the fly. Okay, it's quite quick to do the simulation on the fly, so that we don't waste too much time, too much space on disk, and then possibly it's just quicker to simulate them on the fly than to read the maps from disk. Okay, and so what we do is when we have a noise release, we just create one realization of that, both for the full mission and for the split, and save that on disk. So if you want more, you can simulate as many as you want, but you have to do them on the fly. Okay, so this one realization is mostly just for cross-checking purposes, but you really should generate those on the fly. So, and we are going to look at that in notebooks number 4. So for now, let's just first start to play with maps that are available on disk. Okay, so as we did before, we can choose a channel, and the noise release is the first release that has variable n side. Okay, so in the past we were using just n side 512 and n side 4096, and but for this release instead we decided to change the n side. So the n side is the resolution for the HillPix maps, based on the frequencies of each channel. Okay, so, and you can get this parameter by calling the get default SO resolution function of mapsim. And this is only basically parsing a table that we created, and it's available in the repository. So if you click on this link, so you can see here, which is a CSV table where we have the channels here, and then you see the N side. Okay, so what we decided to do is that for very large beams, we don't want to use too much space, and we want to just simulate it inside 128, and then this is variable, and the top map now are 8192. Okay, which is they're pretty large maps. Okay, okay, so and so we have this. So we're going to access that. So this is pretty standard. And also we have both one full mission. So we basically simulate the 5 years operations of Simons Observatory. And then we also have splits. So we basically split evenly in 4 parts. And so this is very useful for cross-correlating between them. And those are 4 splits that are completely independent. And we can load all of them and we can take a look at them like this. So you see that they have the same scanning strategy we saw before. So now you see that we have an even distribution of observation time. And so the border are a lot noisier. So you see that they are saturating the color map both and the high end and the low end. So there is a lot of noise there. And then the center parts of the patches are instead have a very, very low noise. Okay. And and what are our inputs to simulate this? So these simulations, they do not only contain the white noise of the detectors, but they also contain a simulation of the expected atmosphere contribution. And they are coming from another package, which is SO_noise_models, which is used to simulate what are the expected performance of the instrument. So this is the same figures that were published in the papers about Simons Observatory. And we can access them again through the noise simulation object. So you see, we create a noise simulator object, and then we can call this function, which is basically just a wrapper about that to access those spectra from SO noise models. Okay, and so we can take a look, we can check how they look like. Okay, so you see, we basically have the white noise at IL, and then you see the atmosphere is starting to pick up at lower L's, and then we have a cutoff because our filtering and mapping is anyway going to heavily reduce the power at low L, so there is a built-in simulation capability in SO noise models to do this cutoff at low L. Okay. Okay, and so basically what SO noise simulator does under the hood is get the spectra and then do a simulation with SimFast of this spectra, and then apply the weighting to get a anisotropic noise distribution due to the heat maps, to the scanning of the actual instrument. Okay. Okay, so so we want to take a
sorry, there is a question.
Yeah.
Oh, just I didn't quite follow what you said about why there's no low noise that's at the low end. What were you saying? It's because there's already been a mask applied or something, so it's basically
so the map making process is going to filter all the low L components from the time stream during the map making process, so that it's not going to be in the output map. So when we will have the map from the actual instrument, they will have a similar filter at low L.
Okay.
Yeah, and anyway, they are, of course, we are just looking at a small patch, so we don't have access to the very, very large scale anyway.
Yeah. Thanks.
Yeah. Okay, any other question? Okay, so what we want to do now is we want to just cross-check that the noise power spectra from this map agrees with the input that was this one. Okay, and however, it's tricky because if we just do anafast, so we just do a standard spherical harmonics transform on this, our transform is going to be dominated by the very noisy pixels at the borders. So it's going to estimate a much higher noise power than it should be. And so we need to apodize that. So what we do is we get the heat maps and we multiply our map by the heat maps so that the border pixels that have very low number of hits are going to be down-weighted a lot, and while the center pixels that have very good noise properties are going to instead gain more weight relative to the others. Okay, and so we have access to the heat maps through our software interface. Okay, and of course we can get yeah. And the other correction that we need to do is the sky fraction. Okay, so our spherical harmonics transformation with ANAFAS always averages over the whole sky, and where our map has missing pixels, those pixels are set to 0. So basically you are averaging what's in the signal or with all the zeros everywhere in the map, okay? And so you have to divide for that sky fraction to have the real power in the map, okay? And so we do this transformation, okay? So you see we take ANAFAS of the map, but first we multiply the map by the heat maps, okay? Here I just set ether equals 0 to have a quicker thing, but of course for production runs you wouldn't do that. And then I basically correct for the factor. So I multiply for the heat maps, then I have to divide by the square, and I take the mean. And then I also correct for the sky fraction. Okay, once I have all of that correction, I have a pretty good agreement between the input. So you see the more straight lines are the theoretical ones. So the blue one is for the full mission, and the orange one here is for the splits. And you see that the 4 splits, they gather around the theoretical line for the splits, and the other 2 are here. Okay, the theoretical ones are for uniform sky coverage, so it's expected that the lines in our actual simulations are a bit higher because we have anisotropic noise. We are waiting for the heat maps. Okay, of course you can do a more sophisticated analysis and get better theoretical spectra. But for the simpler case where you just get the spectra out of SO noise models like this, then those are assumed to be for a uniform sky coverage where you spend the same time over all the pixels. Okay. 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 Very good. So we have agreement here. So you see that for the split, I had to multiply by 4. Okay, because it's a 4-way split. So we have 4 times more noise power. Okay. And now we can combine this with what we did before, and we can have a full map which has foreground, CMB, and noise. Okay, and so what we do is basically we take, so we are using the combined map, which already has all the components. So it's just basically missing the noise. And so what we do here, we add the foreground. And so you have a nice map here that has everything together. So you see now traces of foregrounds emission, and together with the weighting coming from the noise, and all the oscillations coming from the noise. Okay, so this is the simplest way to get a map as we expect it to have from the real instrument. Okay, so this includes bandpass integration of all the foregrounds, beam smoothing, and then the noise already after the effect of map making. And so this is a complete dataset that we can use. Okay. The only problem with this is that we only have one realization of this, and so we want to then switch to notebook number 4, where instead we are simulating noise on the fly. Okay, so we already used a noise simulator before, okay, but it actually has a lot more input parameters. So you can, the default should be, the defaults are basically the standard expected mission for Simons Observatory. So you should be fine even just using everything default and just specifying the N side. Okay, so you see here we create this noise simulation object. Okay, and now we have to run the simulation with simulate. Okay, instead of loading stuff from disk. Okay, and this simulate method of the noise sim object is what is doing all the work. So it's going to call SO noise models, get the expected the input, the simulated power spectra, and then it's going to load the heat maps. So if you are running at NERSC, it detects that the heat maps are already stored locally, so it's fine. But you can even run it from your laptop, and then it's going to download the heat maps, which are available publicly through the NERSC web interface. And so it's going to download them on your laptop and cache them locally. And so you can execute this also outside of NERSC. And then this is going to generate the map. So as I told you before, we are simulating this tube by tube, okay, so that we can do the cross correlation between the two tubes. So you specify a tube, and what you get is you get for each tube and for each split. So we're also simulating all the splits at the same time. So for each of them, you are going to get a polarization IQU map with heat peaks. Okay, we'll see later that you can do the same with car. Okay, and so the shape of the map is going to be 4-dimensional. Okay, so the first dimension is the channel that you want to use. The second dimension is the number of splits. Okay, so if you're doing just the full mission map, then you're just going to have dimension 1 there. If you're doing a 4-way split, that's going to be dimension 4. So you see, this is a full map. And then here is IQU polarization, and then the number of pixels. Okay, so if you want to plot a, for example, EE map, okay, then basically you have to get the channel that you want to use 0, and then you want to use the only split that you had 0, and then you want to choose polarized EE, which is 1. Okay, so it's going to be 0, 0, 1. Okay, and this is how we do it. Okay, so you see here coverage is very different because this is a lap. So large aperture has a different scanning strategy. So it's a very wide survey. Okay, so this is the noise that we simulated on the fly, and you can, so we forced a low N side, but if you want to do the standard that we do for our simulation, you should simulate this 8192, but it takes quite a long time. So definitely we don't want to do that interactively. Okay, okay, yeah, so this is the main interface. So you can do loops and call this when you need it, and then free up the memory. Okay, so let's take a look. We want to do a cross spectra of this. So this is a LAT. So for the small aperture in the input, there is no correlation between the channels, even in the same tube for the SAT. As is defined in the SO noise models input that we get. For the LAT, instead, we have this cross correlation between the channel. So we're gonna just check that the cross correlation is as it is expected. So you see, when you do the power spectra, when you get the power spectra, you have 3 components for each of them. Okay, so for the expected polarization power of the noise, we have component number 0, which is the first band in the tube, then number 1, which is the second band in the tube, and then number 3, which is the cross correlation between the two.
Andrea, sorry, can you repeat, please? Sorry if I missed it, the difference you mentioned between the LAT and the SATs for the correlations?
Yeah, so the SAT have no correlation between the tubes, within the tubes, okay?
Within the tube, okay. I'll ask you later.
So you see here, they have cross. So we have an expected cross correlation between the two channels, while for the SAT they are zeros. I don't.
By channel here, you mean single frequency?
A channel is a single frequency, yes.
So we model
channel is a band
between two arrays in a dichroic array, for example, right? But if they're in two different tubes, we don't account for their correlation.
Okay, and I guess that for the SATs, actually, there are only 2 frequencies per telescope. Maybe I'm wrong, but I
right. It might be
okay.
But this is completely irrelevant for the SAT because there are no correlations between any of the arrays, right? But for the LAT, we do model the inter-tube correlation.
Okay, thanks.
Okay, so you see here, we do the same process that we did before. So we have to wait for the heat maps and then correct for the sky fraction. And here we have the EE and BB cross spectra and then the expected input. Okay, so you see same thing here. The simulated ones are a bit higher because they have a unhomogeneous scanning, a homogeneous noise, while the input is just for homogeneous coverage. Okay. Okay, then with the same process, I just want to give an example how you can loop through many different tubes. Okay, so here I'm looping through the tubes, and for each tube I'm simulating maps, and then I am plotting them. So you see here, those are, you see all the different frequencies. So this is ultra high frequency, middle frequency, and then low frequency here on the same scale. Okay, and if you want instead to generate multiple splits, as we did for the release, you specify the n split argument. Okay, and so you need, now the shape of the output has 4 in the second dimension, so you can access them with standard array, NumPy array indexing. Okay, so now the last notebook that I'm going to present, just probably for five minutes, it's going to be about using configuration files from the actual releases and just being able to generate on the fly, not only noise, but also other components. Okay, so first of all, so on the map-based simulations repository, not only we provide the documentation about the releases, but also all the configuration files that were used. So for example, for the noise simulations, you see here, there are some TOML files, okay? TOML files are files pretty similar to the old Windows INI files. So you see it's basically key equals value, and it's a format very easy to use. And this is what are all the configuration of the tool, of the map simulation package to do the release. So if you want to be sure, that you are simulating with all the same configuration of the class, you can directly use those. Okay, so let's see, for example, how you would run a noise simulation using one of those TOML configuration files. Okay, so toml is basically loaded directly into a dictionary. So you see, you do toml.load, and this gives you back a standard Python dictionary. And this Python dictionary is a very general way that I use in this package to configure all the different components. Basically, I have a class which tells me which class I want to use, and then everything else in the dictionary is just passed as it is as an argument to that class. So even if the tool hasn't seen a class before, can still execute it, because it's just going to create a class and then pass everything in. Okay, so so you see, this is a way in Python to unpack a dictionary. So noise config, which is a dictionary, is basically instead passing this as a key value argument. Okay, so now we are configuring a noise simulator with all the same arguments as in the release. Okay. Otherwise, of course, you can just copy paste the stuff from here to the constructor, but this is a bit cleaner, and it's useful if you're using more stuff together. Okay. Okay. So this is a way, and then mapsims is the same. The noise simulation object here is the same that we had in the previous notebook, so you can call simulate and go from there. Okay. Now let's see instead how you can use multiple of those components together. Okay, so let's say that you want to get a noise simulation combined with the CMB simulations and run simultaneously together. Okay, and for this you need to use the mapsim object, which is the actual tool that I use to run the simulations. Okay, so you see, to mapsims, you provide different toml configuration files, and they are merged together in this run. So, and then it's very similar to executing the noise. It's just you call execute instead of calling simulate. Okay, so this execute basically under the hood is going to call simulate for the noise, and then is also simulating the foregrounds, calling PySM to do the bandpass integration and beam smoothing, and then it's going to pass out the result. Okay. Okay, so this is as it is now. This is not very different than what we were doing before. It's just another interface to run the noise simulations, and you see the output. The output is just a little different. It's a dictionary, okay, where it gives you the name of the channel. Okay, but this comes more handy. Oh yeah, another thing that this provides is, for example, automatically writing the maps to disk. So you do a write output equals true, and then has a standard file naming, and this is going to create the maps. Okay, and then we can plot those maps. Okay, yeah, I skipped some cells before, but you can look at them later on. It's nothing too important. Okay, or you see here you can still generate multiple splits. Okay, but the very reason why you would use this system is when you want to merge multiple simulations together. Okay, so this is the most important section of this notebook. So here you see in the length CMB that we saw in notebook number 2, we also provide a configuration for the CMB simulation component. Okay, and what and you see here that I used to run this on Popeye, and so I have a path of the inputs on Popeye, but we can change that to the NERSC path. Okay, and so now we can create another mapsims object which loads both the noise and the CMB in the same configuration. Okay, so now you see that this sim noise object is like a wrapper where it has multiple components joining together. So we have the noise and the CMB. Each of them is their own object. And what mapsims does is can run those on the fly. So you see here, it's getting is simulating the CMB. So to simulate the CMB, gets the ALM and then does the smoothing and with the beam of the channel that we are using, and then simulates the noise and adds the noise in. Okay, so this is very useful if you want a simulation. You see here that there is both CMB and also noise. Okay, and of course, you can go even a step further and also load a configuration for the synchrotron for one of the other components. So you see the synchrotron has a little different way of being configured. So, but you find all of that in documentation. So you specify which model you want to use. So we have SO-specific models, and then S0 is this synchrotron component with spectral index, which is uniform across the sky. And then you run execute, and this is going to run PySM for the synchrotron model, and then is going to, so you see, it's loading all the input component for PySM, so the templates. So it's loading the synchrotron templates, doing bandpass integration, smoothing, and then it's going to call the CMB and do the smoothing as well, and then doing the noise simulation. And this is all available together here. So you see, if you compare this one to the map before, so you see that you have a lot more power coming from the galaxy. Okay, and so you can, we also have a presentation tomorrow about map-based simulations, if you want to know more about this. If there is any question now. Okay, okay, so I'm gonna stop sharing.
All right.
Okay.
Thanks a lot, Andrea.
We'll have 2 more notebooks. Give me a second. Okay, so I'm going to talk about 2 things. The first is more on the fly simulations, but this time focused on making simulations in CAR pixelization, which is the pixelization that we use in ACT. And then I'll also talk about converting a HealPix simulation that's already saved to disk to a CAR pixelization simulation. Okay, so I just want to re-emphasize, the kind of the importance of on-the-fly simulations. If you just think about, what amount of data that we have on ACT right now, just thinking about all the arrays, that ends up being around 260 gigabytes. It's going to be a lot more for Simons Observatory. So if you want to, if you're working on a pipeline that simulates this 1,000 times, it's just not feasible to store all those simulations on disk. So especially if you're working on a pipeline that's involved in some kind of co-adding thing, for example, in component separation, where you're reducing all of these different maps into a single co-added map, you want to use on-the-fly simulations. And so Andrea just talked about on-the-fly simulations using a configuration file interface. I'll be talking about doing this kind of directly from a Python script. Okay, so you can import the necessary modules. A new module here that we're going to start looking at is Pixel. So Pixel you can kind of think of as the HealPy that you would use for car maps, right? So it's a similar library in the sense that you can manipulate maps, but you can manipulate maps that are in many kinds of rectangular pixelizations. So if you want to know more about that, you should watch the tutorial that's linked there. Let me just recap what we just heard a little bit about the noise simulator interface. So there's this nice class, which looks a little bit intimidating, but really the only required arguments is either the end side if you're doing HealPix simulations, or the shape and WCS, which are the equivalent parameters that you'd use for a car pixelization map. And there's a bunch of other stuff which we'll get to in a bit. If you want to tweak the default noise model, say by making it simpler, by removing the atmosphere or making it homogeneous, for example. We can look at those in a bit. Okay, so if you want to make car pixelization maps, the first thing you need to do is to define the geometry that you're working in. And this is the equivalent, again, of like the n side. So then n side 512 defines a helipix map. You can define the car pixelization using a shape and WCS pair. You can construct that just from the nmap module. If you want to construct one that's on the full sky, you can simply specify the resolution in arc minutes. So I'm just using the arc minute unit from the utils module to define the resolution. So once you have that, you can initialize the SO noise simulator. And then the next thing you want to do is ask, how do I generate a simulation from this? And as we've just seen, you need to specify a tube at the very minimum. And since this is an online thing, we'll just work with a simple one, which is lower resolution. We'll work with a sat map, the ST01. So you can ask the noise simulator object what tubes it would recognize. You can explore that like this. So you can see this LT0 is a lat map, for example. We'll pick the ST01. The ST01 has 2 arrays in it, if you find it here. So you can ask the question, what is the central frequency of the first array in the dichroic tube? And it says it's 225 gigahertz. So that's what we're going to simulate. So every time we run a simulation, we're going to get a map that has 2 sets, one for each of these, each of the arrays in the dichroic tube. Okay, so let's run that simulation. The first time you run it, you're going to, as you've just seen, it's going to load some hit maps. And let's examine the output. So that looks like, as we just saw, the number of dimensions in the output can look strange in the beginning, but really it's, so as opposed to helipix, you don't just have number of pixels, but you have number of pixels in the y direction and number of pixels in the x direction as the trailing dimensions. Then the first dimension here is the number of arrays. It's always going to be 2 if you have 2 correlated dichroic, 2 correlated arrays in a dichroic tube. And then you have the number of splits. So the default is just give you 1 split. And you have the number of IQU components, right? The Stokes components. Okay, so let's just focus on the first array in the dichroic tube. So that's 0, and the only split, and then the intensity component, and let's just plot that. So Pixel has some utilities that let you make a plot and then show it on your screen. So just wrap that here. So let's look at that simulation. So this kind of shows you this rectangular pixel layout. It's exactly how it's stored in memory. So that's one of the advantages of using rectangular pixelization. And you'll immediately notice that since we made this on the full sky, it's wasting a lot of memory space by populating zeros in this 30 degrees to the unobserved region of the sky. So if you want to make your simulations faster and you want to make your analysis faster, then you can just work with a different shape WCS template that isn't on the full sky. So you can use a band geometry to define that. And this one we're defining to go from -80 degrees declination to 30 degrees declination, the same resolution. So let's just make another simulation that's the same resolution, but now you can see that the thing that's stored in memory is just this partial sky, and that's what we're going to work with. Okay, so that shows you how to generate the actual simulation. Let me just check if there are any questions. Nope. All right, to understand the noise model that's underneath, it's also useful to just look at another auxiliary product that you get with this, which doesn't vary from simulation to simulation, which is the inverse noise variance. This is a map that's directly proportional to the hit count map that Andre already showed. The inverse variance in each pixel is proportional to the number of hits that the pixel gets, right? And so what this does is it looks at the noise model, looks at the white noise level, and then makes a map of what if you were to imagine the map only having white noise, uncorrelated noise, and on very small scales, what does that look like? What does the variation of that look like on the sky? And you can see the underlying inhomogeneity of the scan here much better. Now what we're going to do is we're going to take this inverse variance map, and then we're going to use it along with our simulated map to verify that the underlying noise model is being implemented here. To do that, we construct this product, which is the map itself, which is simulated, and the square root of the inverse variance map, so times the square root of the inverse variance map. And the idea is that if you take the power spectrum of that map, then the power spectrum of that map should essentially look like a flat line that asymptotes, it should look like a line that asymptotes to 1 on small scales. Because what this is doing is just dividing out the standard deviation at the pixel level in the white noise level. On large scales, you are going to see something that's not flat, and that's coming from the fact that there is 1/f atmosphere in this map. To do this with CAR, you do have to remember that this map that's returned is the inverse noise variance in each pixel. And because the pixel area or the pixel size is different based on the different declination, you do have to make a map of the pixel areas. This is, you can use the nmap function to do that, or you can just access the one that's been pre-calculated inside the noise model, so you can see the variation of the pixel area as a function of declination here. Okay, so let's take the product that accounts for this pixel map area difference along with the square root of the inverse noise variance, and then when you multiply that product, you end up seeing that the map is not homogeneous, and that's because that's the way the noise model is actually constructed. You're essentially making a Gaussian random field of this and then scaling it by the inverse noise variance. So if I take the power spectrum of this map, which I'll do here, and I'll account for a mask factor, which I won't go into right now, that just corrects for the fact that some parts of the maps are 0. You'll find that this power spectrum, this standardized power spectrum, asymptotes to 1 on small scales like they expect it to. Does this actually match the input noise power spectrum that we put into the model? To check that, if you're doing filtering, for example, you might be interested in knowing what the actual noise power spectrum of the map itself is. So you can get that if you pass the same parameters that you passed for the simulate step into get noise properties. You can get the input noise power spectrum. So I'm going to plot that against this, but in the same way that we've divided out this white noise behavior on small scales to make it 1, the get noise properties not only returns the noise power spectrum, but it also returns the white noise level on small scales. So I'm going to divide that out here. So it's the power spectrum divided by the white noise level, and those should agree. Okay. So you can see, again, this is similar to what Andrea showed earlier, but this is just explicitly showing that if you you're implementing the underlying inverse noise variance modulation correctly. Any questions so far? Okay. Something that I found very useful when doing lensing simulations is to simplify the noise model. If you're worried that your pipeline at the current stage can't handle the complexity of the model that's currently implemented, you could, for example, pass in this additional parameters that modify and simplify the noise model. So if you're here, for example, I can just turn off the atmosphere. It's not very obvious how this is different for the sat maps because the atmospheric noise is already pretty low here. But this is essentially just a white noise field that's been modulated by the hit counts. And similarly, you can, if you are willing to reinitialize the class and say that you want a homogeneous sky, what this means is that it throws away information about the hit counts or the inverse noise variance across the sky for that particular tube, and just simulates a map on the full sky or on whatever patch you're asking for, with a noise level that corresponds to observing, using the SO noise model, but observing it at in a sky fraction that you specify. Here I'm using 0.4. And when you simulate that, you can see that there's no mask, there's no hit count variation. It just gives you a homogeneous thing. And you could simulate this on the full sky if you want to test your pipeline, for example. Okay, so this is not in the notebook that's on GitHub right now, but this is an exercise if you want to try it out, which is to play with the white noise RMS argument for the simulate function. The reason that we put this in here is because some of you might not be interested in working with the entire, all the different arrays that we have at all the different cubes. You might just be interested in, what does the noise simulation look like for a co-added map. So while we don't have simulations for a co-added map that's been coded up, what you can do is you can take any given tube, so this particular tube, and then you can scale its white noise level to a value that you think would a co-added map would have. For example, here I'm specifying 4 micropr per minute. And that'll just scale that'll scale the entire noise curve to that new white noise value, and then you can run that through your pipeline. So that's it on noise simulations in car. The next thing I wanted to discuss was generating a CMD signal on the fly in car. So to do this, you can use this class called SO standalone pre-computed CMD. So what's pre-computed here is the spherical harmonic transform of the lens CMD sky. So Alex Van and Glenn ran this, where for a very large number of simulations, I think we have around 2,000 on disk. There are ALMs that are stored that have CMD lensing in them, right? So what this class does is to, it's aware of where those sims are stored on NERSC. It currently only works on NERSC. And then you can specify a tube. The reason you would specify a tube here is because it actually does a beam convolution. You can ask for a simulation of that tube, and it applies that beam on that ALM and then transforms it, and then you can plot that map. I should also note that if you're interested in multiple realizations, then you can pass the seed argument, and you can pass a seed, which is either an integer or a tuple to implement some multi-dimensional seed scheme. You can see here that so I've asked for the simulation on a smaller patch. You can see the ITU components generated nicely here and plotted using Pixel. Okay, if there are no questions, I'll move on to the last notebook of this tutorial session, which is reprojecting foreground maps to cars. So as Andrea talked about, we have a number of foreground simulations, including the galactic simulations from PySM and the web sky simulations, the extragalactic simulations stored on disk. And he showed you in previous notebooks how to access these simulations that are stored on disk. So I'm just doing the same thing here, which is I'm loading up the using HealPy, one of these maps where I'm specifying a 512 n-side dust map, the ITU components for this particular channel. So I think it has that particular beam applied to it, and I can plot that. But you might be working with a pipeline that's working with car maps, and then you want to add this to your car noise simulations. The nice thing is that these are already stored in the equatorial coordinate system. So the transformation, so the way to go from HealPix to car is extremely simple. All you need to do is ALM transform the HealPix maps, so spherical harmonic transform them, and then inverse spherical harmonic transform them onto a car visualization. So that's all this notebook is showing. You first define what geometry you want this to be projected to. So again, it's a full sky geometry with 16 ArcMinute wide pixels. And then I'm doing a HealPix map to ALM, going out to 2 times the n side in LMAX. And then I'm doing a pixel ALM to nmap. It's really just calling libsharp underneath, but it's being projected onto an empty map that has the shape in WCS that we want it to have. Okay, so that's gonna take a little bit of time. Yeah, so it's only this simple if you don't have to rotate from galactic to equatorial coordinates, and so we don't have to because these have already been rotated. Okay, and so now you can plot them in color pixelization. So it's just showing the I, Q, and U components of the dust map at this particular frequency. And then you can directly add that to your CMB sims or to your noise sims, and then run them through your pipeline. That is all I wanted to show.
Thank you, Matt. Questions or comments? Matt, are you able to see the chat? There is one question from Zach.
Yes. Is the pre-computed CMB from the last notebook correlated with the MBS foregrounds? Yeah, so if you're referring to the pre-computed CMB in notebook 6, those are not correlated with the web sky simulations. So that's right. So if you want one that's correlated with web sky simulations, that is a good question. We'll have to look at how you can load that up.
I think that's,
yeah,
that's also in there.
You can, yeah, you can look at the, so that's, let me see, that's in the foreground release. So in the foreground release, there is a CMB component there as well.
Right, since there's only one map of that, I guess it doesn't make much sense to have a code interface. It's stored somewhere on disk. So I think it's documented on map-based simulations on the repository.
Yeah.
Any other question or comments?
Yeah, I have a trivial question, perhaps. If you have a map in CAR projection, is it trivial to make a tangent plane small cutout at any point?
Yes, there are functions to get a postage stamp out of map in Pixel.
And they're in Nmap?
They're in reproject.
Ah, okay.
Pixel.
Matt, you shouldn't feel obligated, but you think you can show that on, like, right now?
Oh yeah, sure.
You have the notebook still up?
Yeah. Let's see. I think I had this in an earlier version of this notebook, but if you want to, let's see. Okay, so let's see if we can do this live. It might fail, but let's try. From Pixel import reproject. And so reproject dot postage stamp is an older version, maybe. So that you can specify the map, and so the map I want to do, take a postage stamp of is map 0, so the I component, let's say. And let's say I want it to be centered at I don't know, 10 degrees and 10 degrees with a width of 100 arc minutes and a resolution of 0.5 arc minutes. Let's see if this works. This module is a little bit in flux, so it might fail, but yeah, we did something. And we're going to plot it. Well, it's a postage stamp. It shouldn't take that long to plot, so. Let's just look at what shape. Okay, let's just try plt.imshow. Okay, well, that's a postage stamp from this, I guess, very low resolution. It's an NSAT 512 map, so I took a postage stamp that's 100 arc minutes wide, so that's why it looks blurry. But yeah, so this is doing it onto a tangent projection.
Matt, there is a question from Zach. When do you use reproject postage stamp versus extract?
Good question. So reproject is going to do some kind of interpolation, right? So if you're okay with doing interpolation, then that's what you should use. The idea of extract is that you want to basically just slice out something from the NumPy array. It doesn't do any kind of reprojection, right? So if you have some other shape WCS that's compatible with the underlying map, which means that you can, it's just a different part of the map, for example, without any reprojection, then that's what you'd use it for.
And I guess it's true that if you had, for example, a point source at declination, say, +50, extract will give you like a small map that with the point source being very distorted, whereas reproject, postage stamp will give you a source that looks like a circle.
Exactly.
Round.
So if you want your compact objects to look like what they would look like at the center of a cylindrical projection, or as they would look in a tangent plane, then yeah, you should reproject them.
Okay, any other question? I'm not checking Slido, but I'm assuming no one is actually writing there. No, okay, great. Okay, well, if not, we actually finished 15 minutes before the scheduled time. Thanks, Matt and Andrea. This was the last of the 4